So sequences are a fairly different sort of construction than really anything else we've seen in this class so far. And before I get into a fairly exacting definition of what a sequence is, I want to start with one of the classic examples of a sequence. That is, we're going to look at these things called the Fibonacci numbers, which were described by the Italian mathematician Leonardo of Pisa in the 13th century, although why he gets credit for them is a bit uncertain, considering there's evidence that this same pattern was described in India more than 1,000 years before his time, but what are we going to do? The Western world likes the Western world. Anyway, for this, we are going to think the way that he did, and the way he thought was, for some reason, in terms of rabbits. So let's say that we have a semi-magical breeding pair of rabbits, and we'll talk about why this breeding pair is semi-magical in a second. Now, these rabbits are very, let's say, consistent. They are consistent in that every month after they are born, they are not only capable of birthing more rabbits, they will birth more rabbits, like I said, very consistent. And they will always birth another mating pair, where that mating pair will also be able to birth another mating pair after their first month. Again, these are somewhat magical in both the sense that you always get that mating pair. They're also magical in that, well, they're usually perfectly consistent. The natural world tends not to be quite so nice, but they pretty monogamistic as well, and very resistant to inbreeding. So all goes well with these rabbits, and if you want to think about a pattern to describe how many rabbits there will be after a certain number of months, well then we're going to start from that one pair, and in the first month we're not going to get any more rabbits because they're still growing up to do there, but then after that first month, that first pair will get us another pair. Then after the second month, that first pair will get us another pair, but the second pair won't be doing much except growing. However, by the third month, both of those first two will be looking at having more rabbits. And then in the fourth, the first two and the third will have more, so we'll get 3 more, and then we'll get 5 more, and 8, and 13, and 21, and it'll follow a pattern something like this to describe the number of rabbits born in a given month. 0, 1, 1, 2, 3, 5, 8, 13, 21. If you wanted to keep going, you'd get 34, and blah, blah, blah. You'd get a whole lot of rabbits, is what you'd really get. Where this list here is what's called the Fibonacci numbers, although why we attribute them to animal husbandry, I'm not entirely sure, but that's where we get them. And that is also called the Fibonacci sequence. Where, as I said, I would give a more exacting definition for what a sequence is a function that maps from a set of integers or natural numbers. But that's not a very useful definition, as it were. It's not a very intuitive definition at the very least. So when I think of what a sequence is, I think of a sequence more as just an ordered list. A list of things that follow a specific pattern. They may go on forever, they may not. We have an idea called a finite sequence, but for this class and in general, you don't study finite sequences very much for the fact that, well, there's a pretty limited scale by the fact that they are finite. There's not a whole lot going on there. So usually when we look at these things, we talk about infinitely extending patterns like with the Fibonacci numbers, like the Fibonacci sequence. Or if I wanted to, I could talk about a sequence that's similarly abstract, but less so. I could look at the sequence of two-dimensional polygons with n vertices. So that would be the point, the line, the triangle, the rectangle, the pentagon, the hexagon, and so on. Or, if I'm thinking a little more numerically, I can define a sequence that I will call AN, where this follows the definition that at position n, let me be a little more specific there, we get the nth digit of pi. So if we want to talk about what these values would be, the value a1 would be 3, a2 would be 1, 3.1, a3 would be 4, and so on, following that pattern, where we call this type of construction there that an, a general term, as it were, because it describes what happens in the nth position directly. Some other notations will call that sort of thing a closed form or an explicit form, because it explicitly gives the nth term in terms of some value n. But we call these general terms in this text, where these are just our list of terms. But usually in this book, and usually with this type of things we're looking at here, we're not going to have these, I wouldn't say abstract examples, but we'll have ones that are a bit more, well, specific and mathematical in their definition, which is the sort of thing we are going to see with our next example.